Welcome back to Computer Graphics and Visualization subject. Today we will discuss Module 4. In last class we have discussed Module 4, that is 3D viewing, right? Today also we will continue with this module, that is 3D viewing. In last class we have discussed how to prepare, how to set our camera, means frame, viewing coordinate frame we have set in last video. That is, means we have set all the camera properties. We have set the camera, then that is P viewing position, then afterwards we have set the viewing direction, that is the normal viewing direction, that is view plane normal, then view up vector, then from that we have derived right hand coordinate system, that is cross product of n, then v, we got x. That way means we have set all camera positions. That's now we are in, after doing that operation, now we are in word coordinate, right? Means we have model coordinate to word coordinate we have transferred in last video. That is, means we have given, basically we have given input in word model coordinate, then all model coordinates we have applied to, we have given input to word coordinate system, then word coordinate system has given coordinates in word coordinate. Now today we are discussing, now already we have points in word coordinate. Those points we have to convert to viewing coordinates. Transformation from word coordinate to viewing coordinate we have to do. That concept we are discussing today, right? In the three-dimensional viewing pipeline, the first step after a scene has been constructed, means in previously we have constructed a scene, right? We have constructed a scene, we have assumed the point, viewing point, then surface normal, view of direction, then x, all those things, then right hand coordinate system we have derived in previously, right? After constructing a scene is to transfer object description to the viewing coordinate reference frame. Now we have to convert viewing description from viewing coordinate reference frame. Now we have to convert the word coordinate into viewing coordinate reference frame. This conversion of object description is equivalent to a sequence of transformations that superimpose the viewing reference frame into the word. Means nothing but our viewing coordinate is somewhere here, word coordinate is somewhere normally, word x, word coordinate x is different, word coordinate y, word coordinate z are different. Then our viewing coordinate x direction, viewing coordinate y direction, viewing coordinate z direction may be different, right? Definitely normally in real life will happen, means we may rotate a camera like anything, then we may capture images. That's why viewing normally viewing coordinate reference frame and world coordinate reference frame are not similar. Definitely they are different. Now what our intention is to map our viewing coordinate reference frame to word coordinate reference frame. Means viewing coordinate x axis has to align with word coordinate x axis, viewing coordinate y axis has to align with word coordinate y axis, then viewing coordinate z axis has to align with word coordinate z axis. That is our intention we have to do here, right? That is word frame. We can accomplish this conversion using the methods for transformation between coordinate system. Then we can accomplish this, there is a method accomplish this transformation from between coordinate systems, right? How we will do normally, right? First step in this is translate the viewing coordinate origin to the origin of the word coordinate system. Means whatever P we have derived in last video, whatever P we have mentioned, that is a camera, the I position or camera, that P we have to translate in such a way that it must align with word coordinate origin. Word coordinate origin means translate that P naught whatever we have in last video we have taken P naught in such a way that must align word coordinate origin, right? Then apply rotation to align the x view, y view, z view in such a way that x view must align with xw word coordinate, y view must align with yw y coordinate, z view must align with zw z coordinate axis respectively. That we have seen in this image, right? Originally that xv, yv, zv are somewhere here, then xw, yw, zw origin is different and that view coordinate origin is different. That what we have done, that we have translated such a way that origin of xv, yv, zv has aligned with xw, yw, zw origin, that has aligned. Then afterwards we have rotated xv in such a way that xv has to align with xw, Then afterwards I have rotated YV in such a way that YV has to align with YW. Then afterwards I have rotated ZV such a way that ZV has to align with ZW, right? That we have written in right side, right? RX, rotation of RX, rotation of RY, rotation of RZ in such a way that all three these viewing coordinate system must align with world coordinate system. That is what in general matrix means. In general, world coordinate to viewing coordinate, world coordinate M equal to world coordinate to view coordinate equal to translate viewing coordinate origin in such a way that it must align with world coordinate viewing origin, then rotate about RZ, RX, that is not RZ, that actually that is RX, then rotate about RY, then rotate about RZ. After doing this one, definitely your viewing coordinate system, viewing coordinate reference frame will align with world coordinate reference frame. This is what happens, right? Then how to do this, right? The viewing coordinate origin is at world position as we have seen in previous video, that is a P naught, normally equal to X naught, Y naught, Z naught, right? The viewing coordinate origin is at a world position, means at a world position somewhere here, right? Somewhere here, that origin of that we have taken is P naught equal to X naught, Y naught, Z naught. Then that you have to translate this translation matrix in homogeneous coordinate system, means minus X naught in X direction, minus Y naught in Y direction, minus Z naught in Z direction, automatically comes and aligns with world coordinate origin, right? This is a translation matrix. Then for the rotation transformation, we can use the unit vectors, like in previous slide, previous video, how we have used unit vectors you can use, because I know that you use nothing but up vector, use nothing but up vector, or you can take x-axis, v is nothing but up, means whatever you want, means if you are taking u is up vector, then v is x, then n is normal, surface normal, n is surface normal. From the composite rotation matrix that superimposes the viewing axis into the world frame, means to rotate we are, instead of taking angle, we are taking a vectors, by taking those vectors, then the rotation matrix is nothing but ux, uy, uz, then vx, vy, vz, means u is x axis, v is y axis, n is z axis, right? This is what we have taken in previous video, like that we have taken. Then where the elements of matrix R are the components of the n, v, x vectors. In previous video we have derived this one, right? Then the coordinate transformation matrix is then obtained as the product of the preceding translation and rotation matrix. Then if you multiply translation rotation matrix, then you will get this as the matrix, that is ux, v, uy, uz, minus u dot product p naught, minus v dot product p naught, minus n dot product p naught, right? This is what translation factor in this matrix are calculated as. Translation factor in this matrix are calculated as the vector dot product of each of the u, v and n unit vectors with p naught. Unit vector is a p naught. That p naught, how we have derived? P naught which represents a vector from the world origin to the viewing origin, means p naught as a vector from world origin to the viewing origin, that we have derived in last class. That is a unit vector, means translation unit vectors, how we have calculated, that is multiply all u, v and n dot product, you take u, v, n dot product with p naught, which is a unit vector. It is from, direction is from world origin to the your viewing origin, that we have derived, means minus u dot product p naught, how we have got, that is minus x naught ux plus y naught uy minus z naught ui, that is means direction of that p naught is from world origin to your viewing origin, that we have derived. That is the what derivation, right? Then after that projection transformation. Now after doing this one, your coordinates are in viewing coordinates, right? Viewing coordinates means you have converted world coordinate to view coordinate, right? Now you have to see that, means all are comes in viewing coordinate. Now that means you are seeing that object. Now from camera I am seeing that object. Now that whatever object I have seen, that I have to project in my film. That I mean, if whenever you focus in your camera, and that means all came together with reference to world coordinate, means everything view coordinate and world coordinate are aligned now. Now you are seeing that one, once that is in front of your camera. Now you have to project that one in your film, that is projection, right? Here projection transformation, that is the next step, is projection transformation. If you see the pipeline, there is a projection transformation. Convert the viewing coordinate description of the scene to coordinate positions on the projection plane, means nothing but now everything is in front of my camera, then I am capturing whatever I will capture, that I have to project in my film, right? Now plane. Viewing 3D objects on a two-dimensional display requires a mapping from 3D to 2D. As I told, now we have to convert actually that object in viewing coordinate is in 3D. Object in viewing coordinate is 3D, that I am projecting on 2D. Means that a film or monitor, whatever if you are taking, if you take a film in your camera, that film is in a 2D. But if you are displaying it in a monitor, monitor is also in 2D. Means I have to convert that 3D coordinate system to 2D coordinate system, that we are doing it in projection transformation. Right now, what is projection? Projection can be defined as mapping up a point P, X, Y, Z. For example, you want to map one point P, that in 3D word, that is in 3D word. Once it is in 3D word, then that is X, Y, Z axis it has. That point I have to map, right, onto its image on the projection plane. I want to map that on my projection plane, right? The mapping is defined by projectors that passes through P and intersects the view plane. Example, you see, I want to map that P is X, Y, Z. I want to project in projection plane or view plane, right? Then I will pass one ray which it is intersecting on my projection plane, that I will draw that point on my projection plane comes there, that is P, X dash, Y dash, Z dash. Actually Z dash will be not there on projection plane because this is projection plane is in two-dimensional, but we will preserve Z for future use, right? Normally P, X, Y, Z, P, X, Y, Z will becomes P dash, X dash, Y dash. There is no Z component on our projection plane because projection plane is only two-dimensional. That is, a projector is nothing but you cast one ray through that point, then where it intersects exactly on your projection plane, there you draw that P, X, Y, Z. Instead of P, X, Y, Z, you draw P dash equal to X dash, Y dash. There is no Z because on projection plane there is no Z, right? This is what we have to do in projection plane and projection, right? Then graphics packages generally support two types of projections. Normally graphics package will support basically two types of projections. One is parallel projection, second one is perspective projection, right? Graphics package will support two type of projection, that is, one is parallel projection, next one is perspective projection. First we will discuss parallel projection. Now we will discuss briefly both, then afterwards we will go individually one by one, right? Parallel projection transfers object positions to the view plane along parallel lines. Means whatever object are there, that object you transfer along parallel lines. For example, this. For example, you want to project this. You want to project this on your monitor. This, is it visible? You want to transfer this on your monitor. Then transfer parallelly. Lines you transfer parallelly, right? Then wherever those lines are, will strike on your monitor, that is a projection plane, then you draw that. That is what parallel projection. In this example we have taken line, that is P1 P2 line. I want to project on my view plane, then I have parallel lines I have passed through those P0, P1 and P2. Then P1 has on my projection plane, P1 has entered P1 dash, then P2 has entered at P2 dash, then I will draw that line. That is what parallel projection means. Whatever object you want to draw, just pass the parallel lines into your projection plane. That is what parallel projection. The parallel projection preserves relative portions of object, proportions of object. Normally parallel projection will preserve relative proportions of object. For example, that original that line is 2 inch, then in your monitor also you will get that line is 2 inch, right? Means it will preserve the proportions of the objects. And this is the method used in computer aided drafting and design to produce a scale drawing of three-dimensional objects. Means this application of this is computer aided design. Then in architects will prefer this one, right? Then there are two general methods for obtaining a parallel projection view of an object. Again in parallel projection, again we have two types of parallel projections. One is orthographic projection, one is oblique projection. Again in parallel projection, again we have two types of projection. The one is orthographic, one is oblique projection. What do you mean orthographic projection? If the lines, the projectors are exactly perpendicular to your projection plane, then that is called orthographic projection. If your projectors are not perpendicular, if they have made some angle with your projection plane, like this, some inclination, if they have made some inclination, instead of coming parallel, If they have come some inclination, that is called oblique projection, right? You can see that is projection plane will be there. If your projectors are exactly perpendicular to the projection plane, then that is called orthographic projection. If projectors are not exactly perpendicular, they have made some angle with your projection plane, then that is called oblique projection, right? Orthographic parallel projections are done by projecting points since we have taken a point, that's why I am discussing with the point. You can project any object. You can project in, it is not only for points, you can project any object, right? As I told this means, if you project, is it visible? If you project all parallel lines parallelly like this, then this is orthographic projection. But if you project from this side on projection plane, some side, for example like this, you are projecting like this, some inclination, that is called oblique projection, right? Orthographic parallel projections are done by projecting points along parallel lines that are perpendicular to the projection plane, right? That is called orthographic projection. Oblique projections are obtained by projecting along parallel lines that are not perpendicular to the projection plane. As I told, if you can see there from my right side image, if you see, then that projector is not exactly perpendicular, that is some inclination. This is what oblique projection, right? Here you can see, right? Orthographic parallel projection. If you take the orthographic parallel projection, then you can see side elevation view, front elevation view, then plane view from top side, right? Those are parallel, means you go and stand side, then you take parallel projectors, right? You stand in front, then you will take parallel projection. You go and at top, again you will project parallel. This is what orthographic parallel projection. In oblique parallel projection, the lines are not perpendicular to the projection plane. There are some inclination, they have made some inclination with the projection plane. That is what oblique projection, right? Then for a perspective projection, then next is a perspective projection, right? Parallel projection in short we have discussed. In next slide onwards it will come detailed, right? For perspective projection, object positions are transformed to projection coordinate along lines that converge to a point behind the view plane, right? For perspective projection, object positions are transferred to projection coordinates along the lines that converge to a point behind the view plane, right? You can see in image, right? P1, P2 line I want to project on my view plane, but how I have drawn? I have drawn P1 and P2 in such a way that there is one convergence point. Then in that convergence point, I have taken my project view plane. On that view plane, wherever those lines it is a touching, there I will draw P1 and P2, right? An example of perspective projection for a straight line segment defined with endpoints coordinates P1 and P2 is this, like this. Means best example I have given. Perspective projection, when you stand on a straight railway track, if you observe with your naked eye, if you observe for a longer distance on that straight railway track, then you will feel that the railway tracks are somewhere they are joined. That is called convergence point. Then depending on where you will take the projection, depending on from your point, means where you stood, from that point to that convergence point, where you take the image, depending on position of that image, then the size of that image will change. Right? If you are taken towards the convergence point, then size of the image is very short. If you are taken the image towards you, then size of image will be bigger. Normally our eye looks in a perspective projection, in a perspective way, right? But perspective views of a scene are more realistic because distant objects in the projected display are reduced in size. As I told, that's why I told example, if you are taken projection towards the convergence point, means for longer distance, at that time the object will be smaller. If you are taken same projection towards you, then you will feel object is bigger, right? This is what projection. Normally our eye looks like this, then our real camera also does like this, right? This is regarding in a brief parallel projection and perspective projection. Then we will go one by one. First one is parallel projection, that is called orthogonal projection, right? Orthogonal projection. A transformation of object description to a view plane along lines that are all parallel to a view plane. Normal vector n is called orthogonal projection, or equivalently in some textbook they may call orthographic projection, right? Parallel projection, orthogonal projection, orthographic projection, all are same, right? Orthogonal projection, a transformation of object description to a view plane along lines that are all parallel to your view plane. All lines are parallel to your view plane, right? That is normal vector in n is called orthogonal projection, or equivalently is called orthographic projection. This produces a parallel projection transformation on which the projection lines are perpendicular to the view plane. As I told, if you are taking projection somewhere here, if you are taking projection of this, for example, if you are taking projection of this, then all edges, can you see this one? All edges will go parallelly. All edges will go parallelly, right? This is what parallel projection. Then if you take parallel projection, only one side you are visible. In this process, orthogonal projections are most often used to produce front, side and top views of an object. As I told, orthogonal projection normally will use, architects will use whenever they want to construct front view, that time they will use front view. Then if they want to the side view, they will come and take side view. Then if they want, they can take the top views, right? This will be prepared by the computer aided design and architects, right? Front, side and rear orthogonal projections are projections of an object are called elevations. Front, side and rear orthogonal projections of an object are called elevations, and top orthogonal projection is called plane view, right? This is one. Then axonometric and isometric orthogonal projections. Axonometric and isometric orthogonal projections. Here, if you go orthogonal, previous one, orthogonal projections, only one side is visible, even though this is a 3D object. This is a box is a 3D object. But if you project parallelly, only one side at a time you can see, right? If you want to see the front side, only front is visible. No other sides are visible. If you stand side, then that side is. If you go top, only top side is visible. This if you go orthogonal projections. But sometimes what happens, I want more sides of an object to be seen. More sides of that object to be seen. Means I want to see this side, I want to see this, I want to see this, I want to see this, right? In that case, we can also form orthogonal projections that displays more than one face of an object, right? If you go orthogonal projection, as I told, only one side at a time. If you stand top, only top you can see. If you stand in front, you can see front side. If you go side, you can see side. If you go back side, you can see rear face, right? But in some of the case, what happens, I want to see more number of faces by using orthogonal projection. That time, such views are called axonometric orthogonal projections. Such views are called axonometric orthogonal projections. Then how to construct this? The most commonly used axonometric projection is the isometric projection. Most commonly used axonometric projection is isometric projection, which is generated by aligning the projection plane, or the object, so that the plane intersects each coordinate axis. Means the plane has to intersect each coordinate axis in which the object is defined, called the principal axis, the same distance from the origin. Means you hold like this, means if you hold like this is a bigger element, you can't see this, right? 1 minute, I will take this, I will adjust, right? If this is object, right? If you see like this, for example, if you see this is orthogonal projection, only one side you can see. If I hold like this, right? If I hold like this, only one side you can see. But when you want to see more number of faces, what I will do, I will hold like this. I will hold like this. Like this. Now how many faces you are seeing? You are seeing this face. 1 minute. You are seeing, I will hold, wait. You are seeing this face. Then you are seeing this face. Then you are seeing this face, right? If I sum like this, if I hold like this face, this face, then this face, then then one more face, this face, means more number of faces you are seeing. If I hold like this, right, that is what axiometric projection. Right, then this and in that case what happens, your principal axis will start intersecting a projection plane, right. Again, one more method of constructing this, we can obtain the isometric projection shown in this figure by aligning the view plane normal vector along the diagonal. Means if the view vector normal, means if you want to take this one, if view vector normal is exactly along the diagonal of this cube, view vector means you want to take a projection here or you want to take a projection here, at that time if your normal is exactly diagonal to this object, then that time also you can take isometric projection, right. This is how to take isometric projection. Then next, then orthogonal projection coordinate. Now orthogonal, that is means only when you want to display more number of faces of any object by using parallel projection, that time only you will go isometric projection. Otherwise, if you want to take orthogonal, then you go for orthogonal projection, which the projectors are always parallel to your projection plane, right. With the projection description parallel to the Z view, with the projection direction parallel to the Z view, always, as I told, always we are looking into parallel to Z axis. Always whenever we are seeing in a parallel to Z axis, right. The transformation equation for the orthogonal projection are trivial, very simple, right. What is that? For any point x, y, z in viewing coordinates, normally in 3D point is x, y, z. In a real world, point is in x, y, z, right. The projection coordinates xp equal to x, yp equal to y. As I told, in this you can see I have taken one x, y, z point, then we have projected on projection plane. As I told, x, y, z will become only x and y, because z axis I cannot retain on projection plane, because projection plane is only 2D, or our screen is only 2D, or your photo film is in only 2D. That time there is no chance of representing z there. That's why x, y, z will become x, y if you are taking parallel or orthogonal projection, right. Orthogonal projection. Then the z coordinate value for the projection transformation is preserved for future use. Means if you want, you can preserve the z coordinate value for future use for determination of procedures, right. This is what orthogonal coordinate. Then clipping window and orthogonal projection view value. Now I have taken my object orthogonal, means I want this object, then orthogonal projection I have taken, I have displayed it on my projection, means it is available in my projection plane, it is available on my film. Then now what is happens, whether whatever orthogonal projection you have taken on your projection plane, do you want to see entire image, or only you are interested in only part of the image? That we have to decide here. That is what clipping window and orthogonal projection view value, right. Here in camera analogy, the type of lens is one factor that determines how much of the scene is transferred to the film. Means lens will tell whether in class, in lab I have taken lens, in lab every time I have given example elephant, right. If you want to see the elephant, then you adjust the lens in your camera in a such a way that it has to cover entire elephant. But there is again one more, if you don't want to see entire element, only if you want to see the tail, then you adjust your camera for the tail. That is what means where you are actually interested, which part of the object you are interested, that you have to decide here. That will be decided in our camera by adjusting a lens. Normally in a physical camera we will do this by adjusting a lens. That's why a wide angle lens takes more of the scene than a regular lens. If your lens has a wide angle, then definitely that will cover more image in your camera. If it is a angle of your lens is very small, then it will cover very less images from the real world, right. That normally our camera does. Then same has to be done in our OpenGL, right, in computer graphics. For computer graphic applications, we use the rectangular clipping window for this purpose. That's why we are told in lab, every time in lab I have discussed clipping window. Means which part of that image, whatever image you have projected by projection, which part of that image you want to see it in your monitor, that we have to decide, right. That is what clipping window, right. In OpenGL we set up a clipping window for 3-dimensional view just as we did for two-dimensional viewing. Again, how we are did for two-dimensional viewing, same way here in three-dimensional viewing also we will set up by choosing two-dimensional coordinate positions for its lower left and the upper right corners. Means lower left corner x minimum, y minimum, x maximum, y maximum, you set the clipping window. You set the clipping window, right? Then afterwards, after setting, right, then next, for three-dimensional viewing, the clipping window is positioned on the view plane with its edges parallel to x view and y view axis. Means its edges are parallel to x minimum, x window minimum is parallel to x, then y window minimum is parallel to y. Means those whatever edges you have set, those are parallel to x view, then y view, right? Window means x side, x edge is parallel to x view, then y edge is parallel to y view, right? This is what the meaning of that line. Then afterwards, right? Then afterwards, then x, y limits are used to form the top, bottom, and two sides of clipping region called the orthogonal projection view value. Now, I have told means x left, x right, y bottom, y top will form the orthogonal project view value. It will form the orthogonal project view value, right? In 2D also we have done same thing. In 3D also we are doing same thing, right? Because projection lines are perpendicular to the view. Always projection lines are perpendicular to the view value. Means x left will decide how much minimum x you want to display. X right will decide how much x maximum you want to display from that projection. Y bottom will display what y minimum you have to consider. Y top will display what y maximum you want to consider. This is what view value. Then next, here we can limit, but what happens in 3D? What happens in 3D? This is what the view value means. Since your projectors are exactly perpendicular to your projection plane, then they may go infinitely inside. Means the length of your projectors are infinite orthogonal projection view value. Means you have taken left, right, bottom, top. Means that's why when your projectors are going infinitely, the length of your projection may be infinite. Right? This can be limited, right? We can limit the extent of the orthogonal view value in the z view direction. Means we are not restricted z view value. We are not restricted to z view. Only we are restricted x, we are restricted y, right? We are restricted y. We are not restricted z, right? That's why z view direction, by selecting position for one or two additional boundary planes that are parallel to the view plane, right? That are parallel to the view plane. Means now in this case, by doing this, nothing but what we are doing, to restrict z also, depth, that is called a depth. To restrict z also, these two planes are called near, far clipping. These two planes are called near and far clipping planes, right? Or the front back clipping planes, or the front and back clipping. Means we have decided left, right, bottom, top. Means x we have decided, y we have decided. We have not decided z. Means how much depth you want to see in that object, that we have not decided. That we have to decide here, right? That is what meaning of second point, right? With the viewing direction along the z, negative z, as I told, we are looking in a negative z direction, because if you take the right hand coordinate system, z is positive towards you, right? Z is negative in this side. Normally we are looking in this direction. That's why always you are looking in negative z direction, right? Axis. We usually have z for less than z near, correct? Z for, actually far is away from my viewpoint, then near is towards me. But what condition says z far is less than z near? Because you are looking negative z direction. When you go from till origin, this is positive. Till origin, this is positive. After origin, z is negative. Right? From origin towards you, z is positive. That's why z far comes this side. Means 0, -1, -2, -3, -4, like this it goes towards negative. That's why z far is less. Z near is towards positive side. That is 0, 1, 2, 3. means that's why the meaning of this is z far is less than z near, right? Understood? Z far is less than z near. Why? Because z far is like toward this side, from origin it goes z far, origin onwards toward this side negative, z is negative, -1, -2, -3, -4. That's why z far is towards minus, right? Z near is towards positive. That's why z far is less than z near, so that the far plane is further out along the negative z axis, right? This is the meaning of that, right? Then next here, then when the near and far planes are specified, we obtain a finite orthogonal view value, that is a rectangular parallel pipe, right? This is what, if you set, already you have set x, already you have set y, now if you set z near and z far, then that will be looks like this, that is far clipping panel, near clipping panel, then already right, left, bottom, top already you have set, that is what clipping volume. This is what clipping volume. Then whatever objects are there in this volume, that you have to display on clipping window. Whatever objects are there in this volume, that object you have to display on a view plane. On this view plane, I have to display whatever object is there here in this view volume, that I have to display here. Where? Here. Right? This is a clipping window. This is x, y, z. But whenever I am displaying x, y, z, whatever object is there from this near to far, that I have to consider, right? This is view coordinate system. This is viewing value, right? Graphics packages provide varying degrees of flexibility in the position of the near and far clipping planes. Means you can adjust this near and far clipping plane can be adjusted, right? In some time you can take, means in some time clipping window may be come within near and, means in between near and far planes. That is a flexibility is there in, as I told, there is a flexibility for adjusting clipping window. Clipping window may come in between far clipping plane and near clipping plane. That adjustment can be done, right? It is not compulsory that always those must be front of your view plane. That is a flexibility will be there in clipping in OpenGL, right? That's why if you take parallel, only if you take two-dimensional, this object looks like this. If you have taken two-dimensional, if this object, it looks like this. If you have taken three-dimensional, means left, right, bottom, top, then near, then far. If you are just near and far like this, whatever objects are there, they will look in this. Whatever objects outside, they will go away, right? That will be deducted. This is what difference between these two volumes, right? Then normalization. Now afterwards, then this is, we have decided in word coordinate. Everything is in word coordinate, right? Means it is in word coordinate. Means that is clipping volume is different. Means those clipping values normally with respect to monitor or something, right? Then that I have to transport to normal coordinate system. Normal coordinate system, that is OpenGL normal coordinate system, we have to transfer. That is normalization transformation for an orthogonal projection. Once we have established the limits for the viewing volume, now we have established the limits for the viewing volume, means some near x I have taken, some far y I have taken, far x I have, means near z I have taken, some near z I have taken, some far z I have taken, some minimum x I have taken, maximum x I have taken, minimum y, maximum y I have taken, decided. That is volume. We have created some volume. Then whatever object comes in that volume, that I have to display. That I have to display on my monitor. But this volume has to be transferred to normal volume, which is available in package. That is a normal volume, right? Normal volume in OpenGL starts, as I told, always -1 to +1 in x, -1 to +1 in y, same as -1 to +1 in z direction, right? That is a normal, right? But our normal, whatever volume we have decided, those values may be different. That's why coordinate descriptions inside this rectangular parallelepiped are the projection coordinates, and they can be mapped onto a normalized view value without any further projection processing. Now these points we have to map to normal value, which is the range. In next comes the range of those normal view value is, some graphics packages use unit cube for this normalized view value. Some graphics packages normalized view value may be unit cube, that is 0 to 1, x and y, that is 0 to 1, or in some other normalization transformation approach, this is symmetric cube with coordinates in the range from -1 to +1. As in our lab example, we have taken -1 to +1, means origin at center, then left side -1, right side +1, then bottom minus 1, top plus 1. We have taken origin, we have considered that is a normal view value, right? Then that whatever view value we have derived near, far, x left, x right, y bottom, y top, that value we have to map to this. We have to map to this, right? That mapping we have to do here, right? Because screen coordinates are often specified in the left-handed reference frame, because normally screen coordinates are left-handed reference frame, means normally positive z is within the screen. Positive z is within the screen, then whatever z is coming out of the screen, that is a negative z. Whatever z coming out of the screen, that is negative z. That is in left-hand coordinate system. In right-hand coordinate system, positive z is towards us, towards viewer, but in left-hand coordinate system, negative z is towards viewer, right? That is what. Normalization coordinate also are often specified in the left-handed system. This allows, then how to do this one? This allows positive distance in the viewing direction to be directly interpreted as distance from the screen. Means this allows positive distance in the viewing direction to be directly interpreted as distance from the screen or the viewing plane. Distance from the screen means whatever distance from the screen is there, that is positive direction. That is positive direction, right? This is what with an example we are saying, right? This is screen, then this is z, again z, this is a z, this is y, then z is positive towards this side, z is positive towards this side, then whatever positive distance, whatever this one directly to the interpreted as the distance from the screen, that is positive distance from the screen. Here object will come this side, means to that I will take this one, then afterwards we will mention this one, that is viewport. Then this viewport I will mention the pyramid, right? Then afterwards, then this we have to normalize, right? Normalization, orthogonal projection, right? Here what happens, for example, this is our view value. We have defined view value xw minimum, yw minimum, z near, then xw maximum, yw maximum, z far. By defining this one, we have defined our view value in viewing coordinate system. We have defined this view value in viewing coordinate system. Then this has to map to this box. This has to map to here, because this is x minimum is -1, x maximum is y minimum is -1, z near is -1. Then x maximum is 1, y max is 1, z far is 1. This whatever value you have here, those has to map here. How to map? Xw min, yw min, z near, I will map to -1, -1, -1. Then this one will map to this. Means these values, whatever point, if it is somewhere here, then at the same ratio, that point has to come here. That point has to come here, right? If that point, if you are feeling that point is at center of this view value, then here also it has to come exactly at center of this. This is normalized view value, right? This is orthogonal projection view value that you have to normalize. Then how to do this? Right? This will be done like how we are done in two-dimensional. Those who don't know, you can refer this window to viewport transformation. We have done it in two-dimensional. Same procedure will apply here. Instead, in two-dimensional window to viewport transformation, we have taken x, y. In this case, we are considering z. Only that is the difference. Otherwise, again, same method we will use. Window to viewport transformation. If I apply that window to viewport transformation, if I simplify, then this is m orthogonal. M ortho means view value to normalization value. M view value to normalization. Then I will get in this position, I will get 2 by xw max minus xw min. Then again there is a derivation. Whatever derivation we have done in two dimensions, same derivation. Then after that I will get transformation. This is transformation. This is scale factor. This is scale. This is transformation. Then by doing this one, I will get this matrix. This is what orthogonal view value to normalization transformation, right? The complete transformation from word coordinate, to normalized orthogonal projection coordinate is obtained by m ortho m normal to equal to m into m word into m, means world coordinate to normalization coordinate we have done. Basically, it was at world coordinate. From world coordinate to normalization coordinate we have converted this, right? At this stage of the viewing pipeline, all device independent coordinate transformations are completed and can be concatenated into single composite matrix. Then all the coordinate matrix means view, world coordinate, view coordinate, projection coordinate, everything can be concatenated, then multiplied, then only can be formed only one composite matrix. One composite matrix. If you take that values of that composite matrix, nothing but you are directly converted from world coordinate to normal coordinate system. This is what how to convert world coordinate to normalization. Means in this video we have discussed how to align, how to convert world coordinate to viewing coordinate, then viewing coordinate to projection coordinate, then after projection coordinate how to clip, then after clipping, then that clipping volume, then that clipping volume to normalization coordinate system that we have converted, right? Means your pipeline last but one stage, then next is device coordinates, then afterwards it comes to device coordinate, then this normalization coordinate, just to apply with the device coordinate, it will display on device coordinate. Means these stages has to occur in graphics pipeline. This is what the parallel projection. Only in this we have discussed the parallel projection, right? In next